On July 8th, Gaster did something that no one else had done in Super Mario Bros. History. He crashed the game in the first level.
Oh! I just got a level! Oh my god!
This was the fastest anyone had ever managed to crash the game, which leaves one giant question: how does it work? To understand the crash, we'll need to investigate an often overlooked feature of the game, the user interface. The user interface, or UI, for Super Mario Bros. May appear to be very simple, as it only displays the player's score, the coins they've collected, what world and level they're in, and the time left to complete the level. At first glance, this is very basic, and you might think that all the game is doing is changing the numbers at the top of the screen as needed, but if only it were that easy. In 1985, the concept of layers hadn't been implemented in game development, so you couldn't create a new layer for the UI and attach it to the camera like they did for Super Mario World. Instead, they rendered the UI to the screen along with everything else, but this solution poses some problems. To render something on the screen, the Picture Processing Unit, or PPU, needs to have access to that object in memory, but since the CPU also needs to update this object, you run into a problem where two pieces of hardware are trying to access the same object at the same time. When this happens, the graphics normally get corrupted, so to get around this problem, the developers set it up so that some things get drawn by the PPU on the current frame, and the objects the CPU needs to access are done in the time between frames when nothing is being sent to the TV. This process involves two variables called VRAM buffer 1 and VRAM buffer 2, with buffer 2 handling all of the map columns that get drawn, and buffer 1 taking care of everything else. These VRAM buffers are key components of the crash, and we'll talk about why they're important later, because now that we know how the UI is drawn, we can look at why the solution also has problems. The entire screen is divided into 8x8 bitmaps, with each square being composed of 64 pixels. As you can see, the different elements of the UI fit perfectly into this bitmap, but getting them to scroll with the screen raises two issues. First, if you just tell the game to draw the UI to the screen, it won't scroll as Mario moves to the right. Instead, it will behave as if it's part of the level and get left behind, as you can see here in this clip. That happened quite fast, but if we look at this clip from the Lost Levels, we see the same effect, as the lower part of the letter D is below the bitmaps given to the UI, so it scrolls with the level as Mario runs through it. Second, let's say you're aware of this problem and tell the game to move the UI each frame so that it moves with Mario. In theory, this is a good solution, but it has a huge problem. Since the UI elements are contained in a bitmap that's 8 pixels in length, you can't move it by 1 or 2 pixels at a time, as pieces of the UI would have to be drawn across 2 different bitmaps, which isn't possible. The only way this solution would work is if the UI moved by a full 7 pixels each time it needed to scroll, resulting in a noticeable jitter, but as you can see from the game itself, this isn't the case. So how did Nintendo overcome these problems? Shigeru Miyamoto decided that in order to achieve greatness, Super Mario Bros. Would need to violate this rule, and the solution is nothing short of genius. All of the sprites for the game are listed sequentially in memory, so anytime the game needs to update a sprite, it will consult this table. But the first sprite in the table is special. Since computers start counting from 0, the aptly named Sprite Zero has 2 special properties. As it's the first sprite in memory, if it ever overlaps with another sprite, it will always have priority and be drawn on top. And because of this fact, the developers created a function called a Sprite Zero hit. A Sprite Zero hit occurs at the moment Sprite Zero is drawn and one of its opaque pixels overlaps with an opaque pixel of the background. So in this case, it would happen every frame that Mario is moving, since the background is full of solid color pixels and none of them are transparent. In the order of operations, a Sprite Zero hit occurs at the same time every frame. So this means the developers will know exactly what happens before and after it. Because of this consistent timing, they're able to use a Sprite Zero hit to adjust the graphics mid-frame without any negative effects, and how they achieve this is absolutely crazy. When it comes to video game graphics, the PPU isn't the only piece of hardware that needs to be taken into account. There's also the CRT itself. When a CRT is sent video data from an NES, it needs to draw this information to the screen, and it does this by using a scanline. Building software that can interact with a CRT scanline is difficult, and this video sponsor Brilliant can help you get a better understanding of the software side of things. Brilliant is where you learn by doing, with thousands of interactive lessons in programming, data analysis, AI, and mathematics. Hands-on problem solving is the best way to learn, and Brilliant works by teaching you a foundational concept, then giving you puzzles and exercises where you see the concept in action. A method proven to be 6 times more effective than passively consuming content from lectures and videos. The hands-on problem solving helps you build real knowledge through doing and not memorizing, and it also facilitates the growth of a daily habit, requiring a time commitment of only a few minutes each day. My favorite course in Brilliant is Thinking in Code, which can help you understand some of the more technical details of things I cover in my videos. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/Abyssoft or click the link in the description. You'll also get 20% off an annual premium subscription. And with that, let's get back to CRT scanlines and how they work. Aside from being the source of the cool effect I have on screen right now, a scanline works by sending information in the form of light from the left of the screen to the right of the screen, starting at the top, then moving down through the rows. This happens incredibly fast. In fact, every second, all 240 color scanlines the NES uses are refreshed 60 times on a North American CRT. And thanks to the slow-mo guys for allowing me to use their footage, you can see what this looks like as each line is drawn in about 2 millionths of a second. In real time, you don't notice this since it happens too fast, but if you record a CRT with a camera, you'll see part of this effect in the form of black bars on the screen, as the shutter speed of the camera is different than the CRT's refresh rate, giving you a glimpse of the scanlines as they're being drawn. So what does this have to do with a Sprite Zero hit? The developers had a theory that since they knew a Sprite Zero hit would occur at the same time every frame, they could adjust the game's camera in between 2 scanlines. Since the scanlines happen so fast, they're able to move the camera without a jitter, as the many slight adjustments create a smooth scrolling effect, leaving us with an order of operations that looks like this. The UI from the previous frame is finished being drawn. A Sprite Zero hit then occurs since Sprite Zero is overlapping with an opaque background pixel. The camera then moves after the last scanline that drew the UI, but before the next scanline has started, with the visual update then drawing the rest of the screen. By following this sequence, the UI is always in the same location as it's sneakily being drawn with the camera. However, this solution requires specific architecture to achieve, and it's finally time we talked about the VRAM buffers. To refresh your memory, there are 2 VRAM buffers, with buffer 2 drawing new columns into the level, and buffer 1 drawing everything else. You might be wondering why these exist as 2 values instead of 1, and as I mentioned earlier, they help split up the rendering so that the PPU and CPU aren't accessing the same data at the same time. However, that's only part of the answer, because Nintendo had another constraint to worry about, and that's time. Back in 1985, CPUs weren't exactly fast, and the time between frames isn't a lot, which leaves a very small window to accomplish anything major in terms of processing. This is the reason why, when the NES loads a new screen, it turns the rendering off completely and all you see is black. It's intentionally doing this so it can have more time to render the scene, as it isn't fast enough to handle everything between frames. The VRAM buffers help manage the rendering time, as only one of them gets cleared each frame, with the game prioritizing buffer 2 since it's responsible for updating level geometry, which means if it has data inside of it, buffer 1 gets bumped to the back of the line. You won't see the geometry ever being drawn, however, as this happens off screen to avoid a situation where the player sees a part of a level that hasn't been created yet. So what you see when playing is only a portion of what's been loaded into memory. The interesting thing about the VRAM buffers is that they aren't incredibly large, with buffer 1 only having room for 63 bytes worth of data, which is about the size of 2 Marios. And by filling up the buffer with more objects than it can handle, the extra data ends up overwriting what comes after it in memory. In this case, the extra data ends up in VRAM buffer 2. Now you're probably thinking, uh-oh, that updates the level graphics, this can't be good. And you're right. Because data isn't where it's supposed to be, buffer 1 now sees the score counter update it needs to do as being corrupted. This causes the game to update 32 tiles in a row, which includes the 6 score tiles and then 26 after the score element. This may not seem like a big deal, but something very important gets corrupted, because Mario isn't Sprite Zero. That's right, I lied to you. I bet you're shocked I would do such a thing, but once you get over that vicious betrayal, you're ready for the truth. Sprite Zero is the bottom part of the coin sprite. Recall that a Sprite Zero hit happens when an opaque pixel of Sprite Zero overlaps with an opaque pixel of the background, and when the coin has its graphics corrupted, it becomes a transparent pixel. This means that a Sprite Zero hit will never occur because the conditions are never met, and since the developers didn't write code for what to do if a hit doesn't occur, as they assumed it would always always happen, the game gets stuck in an infinite loop and crashes. Now that we know why it happens, let's look at how it happens. The first person to achieve this type of crash in an RTA setting was Web2000 when she successfully overfilled buffer 1 by having a coin count that ends in 1 and Mario in large form, then jumped on 2 Koopas in the same frame as Mario bounces into a block with a coin in it. This causes you to gain score 4 times within the same frame, overloading VRAM buffer 1 and getting Sprite Zero corrupted, achieving the crash. However, this crash in 1-2 takes 49 seconds. To see the fastest crash, we need to return to 1-1. Pullover Mania discovered that a crash was possible in 1-1, but the requirements were very tough. With a coin count ending in 1, you need to awkwardly time 2 fireballs to kill 2 Goombas while jumping on another one all on the same frame, with the bounce then pushing you up to activate a coin block. This gets enough score updates to overfill buffer 1, but it was so precise it was believed to be TAS only. Current any % world record holder Niftski would prove that it was possible for a human in August of 2023, when he achieved the crash by starting from a save state, so while not a fully RTA run, he did show that it was possible. Almost a year later, Zen, KZBWZ, and Gaster would look into the 1-1 crash and lowered the tool-assisted time down to 15.5 seconds. But not being satisfied with just a task time, Gaster decided to go for it starting from a save state. On July 1st of this year, he managed to hit it twice with a preset starting position, and a week later, he started grinding for an actual RTA crash in 1-1, and just an hour into his attempts, it happened.
I just got a full level! Oh my god! Oh my god! What the fuck? Oh my god! I did it! I did it! I actually did it! Let's go! Oh my god! Thanks, dog. Oh my...
That's the fastest that anyone has ever crashed the game, and with only about half a second of time save left, this is likely the fastest method that will ever be found. Huge shoutouts to Gaster, -7, Simplistic, and Web2000 for help with this video, and I hope to see you in the next exciting episode of Abyssoft Z.